Welcome to The Explainer. Today, we're diving into a topic that has quite literally haunted humanity for thousands of years. I mean, the Babylonians were struggling with these exact same geometric puzzles millennia ago. But go ahead and grab your mental toolkits, because we aren't just going to sit here and memorize arbitrary rules today. No, we're going to completely unlock the visual secrets behind geometric measurements.
Let me ask you something. Have you ever actually wondered where math formulas come from? We've all spent hours mindlessly memorizing things like 2 bracket L plus B or pi r squared, right? But we rarely stop to ask why those letters and numbers are shoved together like that in the first place. Well, today, we're breaking that cycle of rote memorization for good.
So here's our roadmap for today. We're going to cover 1. Mensuration, 2D versus 3D. 2. Perimeter and area basics. 3. The mystery of pi. 4. Unlocking circle formulas. 5. Quadrilaterals and polygons. And finally, 6. Real-world math problems. Let's get into it.
Section 1. Mensuration, 2D versus 3D. The foundation.
Okay, at its absolute simplest, the word mensuration is just a fancy term for measurement. But what exactly are we measuring here? The really crucial difference lies between 2D and 3D shapes. 2D shapes, like a flat rectangle drawn on a piece of paper, only have length and breadth. Every single edge is entirely visible to you. But 3D shapes, like a cardboard box, introduce this vital third dimension, depth. Because they can actually hold volume inside them, 3D shapes have these hidden edges in the back that you simply can't see from a single angle. But hey, for this explainer, we're going to just master the flat 2D world first.
Section 2. Perimeter and area basics. The core principles. All right, I want you to completely forget about memorizing formulas for a second. Seriously, wipe them from your mind. If you want the perimeter of any 2B shape, just imagine you're taking a walk around the outer edge of a park. Perimeter is literally just the total length of the continuous boundary line forming the outside of the shape. Whether it's a perfect square or some totally bizarre irregular scribble, just add up the lengths of all the outer edges. Boom, that's it.
And this brilliantly illustrates the flip side of that coin, which is area. While perimeter is the fence, area is the grass inside. It's the measurement of the flat space occupied inside that boundary. Take triangles, for example. We all know the area of a triangle is half its base times its height. But here's the kicker. Your base isn't strictly the bottom. Actually, the base changes depending entirely on where your 90-degree perpendicular height line drops. Wherever that straight line lands, that side becomes your base.
Section 3. The mystery of pi. The constant ratio. Now think about this for a second. How in the world do you measure the boundary of a circle when there are absolutely no straight edges to work with? Well, historically, mathematicians solved this by taking a literal piece of thread, wrapping it perfectly around the circle's outer boundary, and then laying that thread flat on a ruler to measure the circumference. They did this for massive circles, tiny circles, you name it. Then, they divided that circumference length by the circle's straight diameter across the middle. And miraculously, every single time they got the exact same constant ratio. That ratio is roughly 3.14, or 22/7. That magic constant is pi. So because circumference divided by diameter equals pi, if we just rearrange that a bit, we discover our formula. Circumference equals pi times the diameter, or 2 pi r. Make sense?
Section 4. Unlocking circle formulas. The aha deconstruction.
Okay, get ready, because this is a massive aha moment. You likely know the area of a circle is pi r squared, but why? Imagine cutting a circle into 16 perfectly equal pizza slices. Now take those slices and arrange them side by side, alternating them pointing up and pointing down. What shape does that start to form? It looks just like a rectangle. And if you were to cut it into tiny, almost infinite slices, it becomes a perfect rectangle. The breadth of this new rectangle is just the radius of our original circle, r. The length is made up of the curved edges, which is exactly half of the circle's total circumference, making the length pi r. So if we multiply this rectangle's length by its breadth, we get pi r times r, which magically gives us pi r squared. See? Math isn't just random letters, it's beautifully logical.
Section 5. Quadrilaterals and polygons. The toolkit.
Now, I know four-sided quadrilaterals can look pretty intimidating, but honestly, they're just combinations of the basic shapes we've already mastered. If you draw a single diagonal line from one corner to the other, your terrifying quadrilateral instantly turns into 2 super simple triangles. By adding the area of those 2 triangles together, we unlock all these derived formulas. For a general quadrilateral, the area is simply half times the diagonal multiplied by the sum of its two heights. Next up, the trapezium. It's half times the sum of its parallel sides multiplied by its height. And finally, for a rhombus, where those diagonals cross at exactly 90 degrees, the formula simplifies perfectly to just half times diagonal 1 times diagonal 2.
So, the big takeaway here is this golden rule. Any complex polygon can be easily conquered by breaking it down into familiar triangles, rectangles, and trapezoids. Seriously, if you see a scary, irregular six-sided hexagon on a test, don't panic. Just draw a few lines to dissect it. It might just be two trapezoids and a square stacked on top of each other. Calculate those smaller pieces, add them up, and you're golden.
Section 6. Real-world math problems. The boss battle. Let's put all of this into practice. Say you're hired to plot a complex park garden. The field is shaped like a rectangle with a semicircle stuck on each end, and right smack in the middle, there's a square house that obviously shouldn't be planted with grass. By applying our visual dissection rules, we can conquer this step by step. First up, identify the core shapes. We calculate the area of the central rectangle. Then we find the area of the two semicircles. And here's a quick pro tip. Two semicircles just equal one full circle, right? Finally, we calculate the area of the square house and simply subtract that overlap from our total space.
If you map out the math using the dimensions from our source material, you literally don't need a single complex equation. You just add your rectangle, add your circle, and subtract the house. The answer? 325 square meters of actual garden space. And from there, you can easily take that final number and multiply it by your landscaping cost to get an exact budget. How cool is that?
Or consider this thrilling case of a trapezium-shaped field sitting between a road and a river. You're told the total area is 10,500 square meters. The height is 100 meters, and the riverside is exactly twice as long as the roadside. Now, we don't have the actual side lengths, but we do have the formula. We treat the roadside as x and the riverside as 2x. We just plug what we know right into the trapezium area formula backward. By solving for x, we prove the length of the riverside is exactly 140 meters. We basically just use the formula like a detective's magnifying glass.
Okay, one final clever trick for you. Imagine you need to find the missing diagonal of a rhombus, but you're only given its outer side length and its vertical height. At first glance, we don't have enough information for the rhombus formula. But wait, every rhombus is technically just a parallelogram in disguise. So we pretend it's a parallelogram first and use base times height to find the total area, which gives us 24. Then we take that 24, plug it backward into our rhombus diagonal formula, and boom, we solve for the missing piece. A clean 6-centimeter diagonal unlocked simply by shifting our perspective.
You see, you now have the power to understand math conceptually, rather than just blindly memorizing a textbook. Everything we've covered today, from wrapping threads around circles, to slicing them into rectangles, to carving complex polygons into simple triangles, it all proves that formulas are not just random magic. They are pure visual logic. So, I leave you with this thought. How will you look at the architecture, the parks, and the everyday shapes around you differently now that you know the hidden math constructing them? Think about that the next time you walk past a fascinating building. Thanks so much for joining me on this explainer, and as always, stay curious.